We're working on limits now, and this is a good review. I wish we were at school. It's a quite extensive review, and there's a lot to remember. So you need to take quite a bit of time with this lesson. Okay, so on the exam, you should be able to compute them, limits algebraically from a graph, know the relationship between asymptotes and limits, discover the limit definition of the derivative. That's really, really important. This stuff, you need continuity algebraically and graphically, know its relation to the limit, and L'Hopital's rule. So let's look at some theorems. The limit of a constant is just that constant. The limit as x goes to c of x is just c, like this is just like a straight line. If you have a constant in front of a function, you can factor the function out in front of the limit. If you have two limits added together, you can split or subtracted, you could split them up. If you have two limits multiplied, you can split them up. If you have two limits divided, you could divide them. And if you have them raised to the power, the limit can go inside the power. And if you have them raised to the square root, the limit can go inside the square root. Okay? So then let's look at, a lot of times we can do these very fast by using dominants. So you need to remember that, and we're talking about on the bottom, which is if it's larger on the bottom, in dominance. Okay, so let me rephrase that. If the bottom is more dominant, then it equals 0 than the top. Okay, so that means that exponential functions will be the fastest. They're the most dominant. Then comes polynomials, and then logarithmic are the least dominant. Okay, so sometimes all you have to do is look at, you have one kind of a function on the top and another kind of a function on the bottom, and you can figure out it pretty fast using dominance. And don't forget the limit squeeze theorem. Now that usually comes up where we have like the limit, if you look at this, it's say we have the limit as x goes to 0 of x sine 1 of x. So we want the limit of this. And we don't know a way to do it. So what we say is, we can use the squeeze. We know that the limit of sine x has to be less than 1. I mean that the function sine x is less between 1 and -1. And then we know that the squeeze theorem says that if we have a limit and we take it from the left-hand side and the right-hand side, and there's a function in between, it squeezes it down. So let me say what I'm going to do. So this means that I can go, if I want this x1 over x, I can say that -1 over x is less than sine x. So let's see. I meant to do this. Sorry. Go back, Mary. Okay. So we have sine of 1 over x. Anything sine has to be less than 1 and greater than -1. So it's okay to have sine x. And now if I multiply this side by x, do you remember this? And then I have x sine 1 over x, and that would be less than x because I'm multiplying this by x and this by x. So we know that that's true just algebraically. And we know the squeeze theorem says that if I take the limit of the first one, x going to 0, whatever it's going to, from the left of a -x, that's equal to 0. And the limit as x goes to 0 from the left of x is equal to 0. And so then if this function is between those two, then that means the limit as x goes to 0 of x sine 1 over x equals 0. So if you get the left-hand side limit and the right-hand side, and I don't mean left and right limits, I mean the left-hand side of the squeeze theorem. All right, so you can look back in your notes on that, and we'll probably have some examples.